Well, you know.
Hello, everybody, and welcome to the final edition of this semester's Applied Stats Workshop. Dana is out of town. I'm covering for her today, but today we're very pleased to have Jeff Gill, Distinguished Professor of Department of Government at WashU St. Louis. He's a visiting scholar here and the editor of Political Analysis. Please take it away.
Thank you. Thanks for coming. Dana was really desperate for a speaker, so I filled in. I wasn't her first choice or even her third, but anyway, so I want to talk about this project today. And the first thing I'll tell you is I need a better title. This is the worst title ever, and it's like the third version.
You put the little.
I'll just speak louder.
Oh, no. It's actually recording.
Yeah, we had a long conversation
Okay,
about
so you're
that.
good. All right, sorry.
Yeah, I'm loud. So, and so this project started 8 years ago, roughly speaking, and George Casella and I got a grant for this. So that sort of the core of what I'm going to talk about today is collaborative. And that was winter-ish of 2011, and then unfortunately he died June of 2011. And I kind of worked on it a little bit that summer and then threw it in the file drawer. And so what I'm attempting to do is to resurrect it and bring it back to life and improve it. And so it's a great opportunity for me to talk about it today. It's actually based on this series of papers, and I'll talk about some of the technical content on future slides. But we first realized that when you put a Dirichlet process prior on a random effect in a regression style model, that you can soak up some of the latent information that makes your model worse. Then we realized it actually produced better parameter estimates in terms of the uncertainty. And then we attacked this precision parameter, which the literature had struggled with. And then we did a bunch of stuff to improve the computational aspects of it. And there is, in fact, an R package for all of this. But this is going to be the last paper in this series of papers. And so it was a great run. I'd like to have one more paper out of that. It would have fit in sort of here somewhere. So what I'm going to do today is I'm going to take this Dirichlet process setting, which I'll describe today, and that's going to produce subclusters, which I'll talk about. And then I want to complement that with a totally independent structure that'll produce actual substantive clustering, or estimates of actual substantive clustering. So there's two orthogonal dimensions to this. The starting point is the usual random effects specification, where you have psi, or in Gelmanese, that's a pitchfork. I'm going to replace that with the Dirichlet process on the random effect, okay, in such a way that that random effect gathers up on each iteration of a sampler and manifests it in terms of the set of subclusters, which makes the model fit better. So the result is going to be fewer assumptions, better estimates, that is, shorter credible intervals.
But substantively, what's the difference?
Between what and what?
Between the cal n and the cal dp.
So this is something that you would estimate in a conventional sense, right? If you knew groupings, so you can bin cases into categories, then you can assign those categories unique random effects. This is going to happen under the covers, more or less, on each iteration of a sampler. And what it does is it's sensitive to information that's in the data, but not expressed in obviously column ways.
No, but the first one just says phi comes from a normal distribution, mean zero. Right?
Yeah. Oh, I'm going to describe this in excruciating detail, Gary.
Oh, okay. Okay, it's a thing.
In fact, it's a thing. Yes. In fact, that's a good setup for the measure theory. So y is a conventional outcome variable that we care about. It takes on values in the measurable space curly y, curly b, where curly y is an arbitrary, the support of y, and curly b is the abstract space. Okay, now here comes the big leap in this literature. That is, the parameter of interest is not beta or theta or something like that. It's the unknown probability distribution that's appropriate here. So that is, it's a random probability distribution, not a random variable in the conventional sense.
Oh, wait, you specified, so can you just go back one page?
Yeah.
I apologize. So you specified two perfectly reasonable statistical models, right?
Yeah.
I mean, In fact, both of them are linear statistical models
Yeah,
with one extra parameter.
right.
That probably needs an eye on there, but anyway, psi, and so these are substantive. You make they're Bayesian models where you make an assumption. So the first case, that random effect is normal. And the second one, it's something else. And I'm just like show us a picture. You know what I mean?
There is a picture in your future.
Okay, but there's no problem. You're not making an inference about a probability distribution, right? It's an assumed probability distribution, isn't it?
Sort of. Give me 10 minutes.
Okay, you got it.
I have a much simpler question.
Yes.
Yeah, 10 minutes. Jeff was keeping track.
Okay.
Shorter credible interval on the fixed effects or something?
No, actually, yeah, on the betas, on these regression coefficients. That was actually a surprising result we didn't anticipate, because all the action is going to be on the substitution of the random effect.
What was the question? I'm sorry.
The question was, these shorter credible intervals, where do they pertain? And they actually show up on the betas that you care about, even though the work is on the random effect.
Even if your true data generating process, or credible intervals, okay.
But in the simplest terms possible, you're just estimating instead of one random effect, you're estimating a mixture of distributions of random effects.
Yeah, and then we're averaging over that distribution numerically. So it averages out. So it's ephemeral, but it makes the model better.
It's ephemeral?
Ephemeral in the sense that each iteration of the sampler, I'm getting way ahead of myself, produces a different set of configurations of random effects. So here, you do this because you know who belongs in what group. I don't know who belongs in what group. Okay, so this is the big leap here, that is that we don't know the exact distribution, but I'm going to average over a family of distributions, and you can actually average over all distributions if you want. It's just harder. So define curly S as the sigma field generated by the p's, such that p of a is less than r for all a's that are subsets of curly b, and r is between 0 and 1 space. So this takes it from an abstract measure to a probability measure. Now define nu, that's the probability measure on curly p, curly s, which is going to be a prior on the unknown distribution. Right? What we really care about, though, is nu star, which is the posterior of that conditioning on the data. There it is, right under my arrow. Okay, so it turns out nu is a Dirichlet measure if for every finite partition that you can plot down on this space, you get a Dirichlet probability structure. So here's just the kernel of that. So this is an important result from these papers. Ferguson and his student Antoniak, who introduced this idea. And there's a really interesting sort of history of science story behind that, which is that in those papers, they worked out all of the measure theory, which is reasonably challenging. They demonstrated that the result of this conforms to Kolmogorov rules, which was challenging. They're dense papers, they're mostly in annals, and there's no data, 0. X1 through Xn is the data. And the reason is they didn't have the computational tools to actually go run the model that they were suggesting. Okay? And so along comes Bayesian stochastic simulation, and it's a perfect recipe for that, as I hope you'll see. So we're going to notate this, where G0 is a base distribution for this unknown random distribution. And you can kind of think of that sort of as the expected value. And then there's a concentration or precision parameter, lambda, which is the variability around the cylinder defined by G, or G0, excuse me. And together they're called the base measure. And so we have this prior specification where G is distributed Dirichlet process with those two parameters. All right, and it's the collection of all probability measures on that curly y, curly beta from the last slide. And so here's just a restatement. So for any finite, where k is obviously the finite parameter, the joint distribution of these probabilities is Dirichlet, right? We're now specifying the partitions with the Dirichlet statement. Okay, so another important paper. Oh, I'm sorry, I'm not quite there yet. Since these things are, when you plop down that partition, that is when you partition out the cases into these subclusters, what you get is this countably infinite mixture. there's a set of important early papers there. The key, though, is this Blackwell and McQueen paper, where they find that if G is a Dirichlet process on these random effects, in our case, then the marginal distribution is a Pouillet process, which I'll describe on the next slide. But the important part is that it's got this serial nature built into it, where the distribution of psi I is conditional on the prior psi's that you've already stipulated, according to this weighting here. And the key to this weighting here is lambda. So lambda is that concentration parameter. So when lambda is big, obviously that part goes away and this part is featured. And it's important because of the way the algorithm is set up. And again, this is Ferguson. So the Pouillet process in this context is the so-called restaurant algorithm. So it works like this. So the first diner, the first case, you put at the first table. Okay? Then the next diner comes in, or the ith diner, and they sit at the unoccupied ith table with this probability. Okay? Or they select one of the previous tables that are occupied with this probability here. Hence that mixture on the last page. So now once you do that, the table locations are this dependent exchangeable sequence. It's dependent because they're serially drawn, and it's exchangeable in the classic Di-Finetti-esque Bayesian way. Okay? So now we have an expression of those partitions on that sample space. Okay, so the idea is in the sampler, you do this on every iteration, right? Then you average over those, and what you've done is you've averaged over the family of distributions that you specify. So at the end of the day, right, we have our y's, which are conditional on some set of theta parameters, whatever else we're up to. And then the series of psi 1 to psi n, which are non-unique because each table gets a psi, gets a random effects component. It turns out you can express this thing in a standard likelihood way, except it's a really awkward likelihood function. It's worse than it looks here. And Liu and Lowe independently worked on this problem. And the problem with this likelihood function is, well, first of all, it's difficult analytically to take the integral over the size. Obviously, we'll do it numerically. And then this part here, this is the set of clusters, such or subclusters in our language, such that the cardinality of C is K. So you're producting up all the cases within each cluster. And that is just a really unpleasant likelihood function to work with. Lowe in particular, I don't know, this is 80s, yeah, wrestles with it. And it turns out that the concentration parameter, the MLE on this is almost impossible. And so that's not a problem in the standard Bayesian stochastic simulation setup because we don't care if it's got multiple modes and things like that. We're just going to go describe it. So C is this partition, right? The y's in each group, and then of course we have the size involved. Okay, so one of the first things we noticed computationally is, well, the sampler is really slow. It's doing a lot of work. So one of the ways we found to speed it up was to reduce the work on the bookkeeping work and so on and so forth on these subcluster assignments, these table assignments. And so imagine a subcluster assignment like this where the first two cases are in this one, 3, 4, 6 are in this one, and 5 is in that one. Well, that gets expressed in a matrix, or a matrix, such that, right, this is the first subcluster, here's the second, here's the third, right? And so what it means is that we can now estimate a smaller set of units at the same time, rather than cranking through all n of them, even though some of them are non-unique. So to continue my contrived example, right, psi is going to get mapped to eta through the matrix A, in such a way that we have fewer things we have to worry about. So that's a bit of bookkeeping, but it turns out to be really important in the efficiency of the sampler. Okay, so now when I incorporate the A matrix, right, I'm going from a structure like this where the psi I are going to be Dirichlet process with lambda, and I'm going to average over all normal distributions with mean 0. Now, that's just a selection. I could have picked other distributions. As I said, in the Ferguson paper in particular, you can do the entire universe of distributions, but practically that's not very easy or even important. It's theoretically interesting though. So when I introduce the A matrix, right, instead I have this structure here rather than that structure there, which is easier to work with. And if I could marginalize all of those etas, I'd have a nice closed form statement for the distribution of Y. X.
So the dimensionality of A, though, is changing every draw of the sampler, right?
Yes, that is correct.
Okay.
Okay. And that's important, actually, because that allows you to average over wide classes of distributions. Okay. So the literature is a little tortured on this point, but this is the truth. A typical strategy that you can find, even in stat journals, is people will run this, and they'll notice that case 1 and case 12 will set at the same table a lot in the restaurant algorithm, and they'll sort of engineer these things around in different ways to create actual clusters. Well, that doesn't work at all. First of all, the subclusters are not in any way substantive, okay? They're there to make the model fit better. They're there to account for latent heterogeneity, okay? So I said that, let's see. They don't reflect anything from the covariates other than just the heterogeneity that pops out. And they're simply there to make the model fit better. But here's the big thing. There is no penalty for overfitting. That is, there's no penalty in the model for lots of table assignments, okay? Now that lambda parameter, which either gets fixed by some people or estimated by others, will dictate that to a great degree. But there's no reason that it doesn't want to shove lots of people at different tables. So we first noticed that in the bottom one, the JAS article, we were looking at political executives that had been nominated by the president and approved by the Senate over a 20-year period. And there were about 500 of them. And on each iteration of the sampler, we were putting them at about 225 to 250 tables, somewhere in that range. And we know there are not over 200 types of political executives in the United States government, right? Now there's like one, right? And he's being investigated. Okay, so keeping that in mind. So now having locked that part of the model down, I want to now redirect it and actually go after substantive clusters in the data, okay? So one way to do that, which is not the right way, is a mixture model, right, of some sort. And so this is just to remind me, right, that a mixture model doesn't actually identify what cases go in what clusters. It simply weights the cases according to some configuration, okay? So I prefer this product partition model, which is from this guy Hartigan at Yale. So it basically says you have some defined C on each iteration of the sampler, which actually puts people in potential clusters, right? And then you test it with a metropolis step. And so what we have is we're producting over the i's in C sub L, that is cluster L, and then we product over the clusters, right, for a regular likelihood function statement.
Could you restate the case against mixture models? Because they are so common.
Oh yeah, I mean, no,
finite and infinite.
I love mixture models, they're great. They're just not useful for my purpose. Okay, so the next two slides, I'm going to denigrate mixture models for my purpose, and then I'm going to promote product partition models for my purpose. So I think I'll answer your question in that context.
For both infinite and finite mixture models. Like
Yeah. Well, yeah, I didn't really worry about the infinite case, but
okay.
So here's reasons for my purpose. Remember, I want it at the end of the day. I want the probability of certain clusters, right? The posterior probability of that cluster configuration or that cluster configuration. So first of all, the mixture model doesn't have a parameter that identifies clusters. It just averages over cases. Okay. That is, let me go back. This might be part of your question. That is, every y gets a set of weights, right, that you estimate or define. It doesn't say that case 17 belongs in cluster 3.
But you can, I mean, what Kosuke and I did on finite mixture models and theory testing, you could model pi as a function of other covariates.
That's true. Yeah, that's true, and I do know that paper. I don't think that helps me today.
I don't think it will either.
Yeah. So yeah, modulo that. Okay, I want an actual parameter or configuration. That is, I want a cluster identification. Okay. The other thing that people often do, right, is they decide there's a certain number of clusters, then they go estimate, and So how many times you've seen the galaxy data estimated? It's either 2, 3, or 4 clusters, depending on who you read, right? And then people are still arguing about that, I think. Also, in the Bayesian sense, a mixture model has the label switching problem. That is, it's not invariant to the switching of the subscripts on the cases with a symmetric prior. And that's actually a really big problem for me in this case. Now, the reason I like the product partition, right, is it's reasonably computationally efficient, given the literature that I'm in, which is to say not very efficient given other literatures. The model you see today takes about 5 days. I can actually set up a model to move between different clusters, that is, different cluster sizes and number of clusters. The key paper here is this Booth et al. Paper that says that I don't need to use RJMCMC because the bijection function is imposed by the algorithm. We get a cluster identification, and we're not susceptible to the label switching problem because we identify the cases that are in the clusters at that moment of the algorithm. So I really expected a question there. Oh, did that help?
Yeah.
Okay, that's what I meant. I think you anticipated these two slides. Okay, so in addition to the Dirichlet process prior component, right, we're going to search for a cluster configuration. Once we have a cluster configuration, inside each cluster, we're going to run a linear model. So this is the Lth cluster, right? So these are going to be distinct beta Ls, okay, where everything you see subscripted L is for the Lth cluster. So it accounts for the latent heterogeneity, and it accounts for the fact that there are clusters that you can identify in the data. Okay, so these don't nest, these are orthogonal. Here comes the worst graph in the world. Okay, now I'd love suggestions for how to redo this, but this is my point here is to show sort of the orthogonality of it. So imagine the yellow lines identify clusters in the data, and the green lines identify the subclusters in the data from the Dirichlet process. So what does it mean? It means this case and this case, they're in the same cluster, the same substantive cluster, but they're in different subclusters, different table assignments by the Dirichlet. But this case and this case, they're in the same subcluster, but they're in different actual substantive clusters. And so every time I show this, people don't like it. You're allowed to not like it. I can't figure out a good alternative for saying that graphically. Okay, so yes, see, here comes the objection, Chris.
No,
Oh, sorry, I didn't. I
don't
just heard
understand
from over
enough
here.
to object to anything. But you're running a regression in each of your subclusters. So you're saying at a specific
No, each cluster, not subcluster.
each cluster.
Yeah.
How do you figure out what your clusters are?
Okay, so the Dirichlet process is going on at each step. In addition, we're going to propose a cluster configuration, right? We're going to have a cluster configuration query. Do you want this one, right? In sort of in exactly the Metropolis Hastings sense. And then we're going to accept it or reject it. Do we want to move from the current cluster configuration to the next cluster configuration?
This is independent of the subclusters of the Dirichlet.
Totally independent. That's the confusing part, and I'm trying to make it as clear as possible on the paper. But one thing I can do is I can drop the language of subcluster, I think, which some reviewers previously didn't like, and call them. The literature doesn't have a well-defined name for them.
What is the Dirichlet process doing for you in terms of your clustering if you're not using the subclusters to build your clusters?
So the subclustering from the Dirichlet process, that is soaking up latent heterogeneity that's unrelated to regular substantive clustering. And then we pick up regular clustering
So
from
Dirichlet is all residual stuff.
You could think of it that way. We're basically averaging over this family of normals to account for the latent heterogeneity that's not parametrically specified. Hence the term non-parametric Bayes, which is like the worst term ever, right? Because being Bayesian is very parametric. But it's the idea that I've got this class of normals with mean zero, all normals with mean zero. And I'm going to average over it and therefore soak up that latent heterogeneity I can't model parametrically.
Wait, but your tau is a hyperparameter on your base measure. Are you fixing tau or are you putting?
I'm going to estimate it.
Right. So then so your base measure is normal, but you're actually looking at only a distribution of point masses that.
Okay, so
it's going to be an infinite number of little point masses.
Yeah.
Which is what the data.
Well, however many cycles of the chain I run.
Right, so I don't understand what you mean by saying you're averaging over all possible normals.
Well, I'm averaging over all possible normals that I can simulate, which is a lot. So you have a tau parameter bounded by 0 and positive infinity, and I'm going all over that with 10,000, 50,000, 100,000 draws. So it is an estimate. It's a numerical integration, exactly.
Okay.
So can you, like, what, so an alternative approach is to try to, like, take the interstate process and, like, penalize it for overfitting.
Yeah.
And try to, like, get the, do the substantive clustering and the residual clustering.
If you could figure out a way to do that,
Okay.
that is a viable option.
Okay.
And I never figured out a way to do that I had confidence in.
Yeah, because I've known, like, when I use stuff in the over time case, it's somewhat easier to build in
Like a learning
stickiness,
mechanism.
basically a stickiness
Yeah.
in, like, the transition probabilities. But I understand for non-temporally ordered data,
Yeah.
that might not be, it's hard to know.
Yeah, what I worried about there, Matt, was that is it still an ergodic Markov chain,
Yeah.
right? Because you are fundamentally changing things as the chain runs.
Yeah.
And that could probably be solved.
Yeah.
But I did this instead.
And sorry, the cardinality of C, that M is not fixed, or is M fixed in advance?
It is not fixed, and I'm about to get to that in about 5 minutes.
Sorry, could you go back and talk about what it means concretely for latent heterogeneity to not have substantive meaning? Like what is
Well, it doesn't have measurable substantive meaning, right,
Sorry.
that you can pick up. So if I could give you the exact set of random effects just as a gift and not tell you where they're from, you take it, right? So what I'm doing is I'm basically averaging over a family of those. Not basically, I keep saying that. I'm literally averaging over a family of those. Okay, so so to set up the Bayesian model, I'm going to be as conjugate as possible to make my life easier. So within each cluster, right, I'm estimating a beta L vector centered at beta naught, right? And then I have sigma squared L and a locally scaled precision matrix that everybody shares S. Okay, so no matter what cluster you're in, you still get the same S. Then sigma squared L gets an inverted gamma. So here's the Dirichlet process set up, right, which we've seen. Normal around 0, tau squared is an inverted gamma, and I'm giving lambda a gamma prior. Then we get to the product partition part, right? So that's the same things up there. Here's the inverted gamma, and then S gets a Wishart, where B is just a diagonal. I saw no reason to worry about the off diagonals. If you can think of one, I'd love to hear about it. And I give each diagonal a gamma prior. So this is a set of priors. It's as conjugate as possible. But how do you set up a prior on C, the cluster configuration? And that's really the weird part, is to think of cluster space as a random variable, and which I'm going to do in a minute. So if you could identify all those components, the y's inside each Lth cluster would be multivariate normals, well, I'm sorry, t's. And if we could do the complete process, right, you'd see something like this. This is just a definitional statement. I haven't specified some of the inside of that yet. But the problem is putting priors on clusters. And so this turns out to be a lot trickier than you would think initially. So here's an example where I just have 4 data cases, okay? And so if I've got 4 data cases, right, I can have 4 cluster classes and 5 configuration classes. So here's a cluster class where they're all in the same cluster, and here's a cluster class where they're all in their own cluster, all 4 cases. And then you can have a split of 2 in different ways, right? 1 3s or 2 2s, and then you can have the 3 clusters with different permutations. And so this B and P, that defines the partitions of the integer n into P components. So B41 is 1, B42 is 2, and so on and so forth. That's just 4 data cases, right? And so that generates 15 different possible clusters according to that typology. Well, that doesn't sound bad until you start ramping it up to real data. Okay, so for this n of 4, right, I had cluster classes 1, 2, 3, and 4 generating, right, these configuration classes, which generated these partition types. Okay, well, it turns out the number of partition types for given n and p is a Stirling number of the second kind. So you go running for Abramowitz and Stegen. Do you know this book? It's a gigantic phone book looking thing of math recipes, right? It's really useful to have around. Chris is nodding yes. Now you can get it on a CD-ROM. Anyway, so this just defines the number of partition types. Okay, that's not bad news. Okay, the bad news is that the total number of possible partitions is a Bell number. Okay, now Bell numbers are gigantic. Okay, I mean like unwieldy gigantic, essentially infinity. So if you put the number 30 in here and turn this crank, that would be more than the number of estimated stars in the universe. 30 data cases produces more partitions than the number of estimated stars in the universe, which is 2.4 to the times 10 to the 23. That's just estimated, right? And so that's the size of my sample space for the clusters. I'll come back to that problem later. It's also interesting that the Bell number is the sum of the Stirling numbers of the second kind. So this is a really interesting, very geeky permutations and combinatorics literature that's fun to poke around in. This just says things grow fast. So here's the prior I'm going to use. It's from this 2014 paper, which didn't exist when I started this, so I had other less effective alternatives. And it's a hierarchical prior because it's a recipe, basically. So first, put a distribution on M, the number of cluster classes, which is Poisson. That paper defaults it to 1. I've been playing around with that parameter. Okay, that says, okay, now I'm going to have this many clusters. Then generate, once you've got this M, right, there's a set of partition types, according to the recipe on the last page, and then just uniformly pick from one of those. Okay, so this is a slightly awkward prior in the sense that it's got multiple steps, but that's not hard to implement in software, obviously. And so for a given partition type that pops out of there, you have this multinomial count, where that thing here just makes sure that we don't double count things like y1, y2, and then y3, y4 versus y2 and 1, y4, y3. Right? Because these are the same partition. Okay? So now we have a recipe for that. So if we were able to, and which we're going to do numerically, right, integrate over beta naught, integrate over eta, integrate over tau squared, integrate over sigma squared, integrate over the v's, integrate over s, then we would have a posterior probability for a certain cluster. And that's what's going to pop out of the sampler. Okay? I'll return to this, but everything now to the example is about the sampler, the estimation process. So that's all the setup in only half an hour.
So the last bullet seems...
Yeah, so for the moment, the betas are simply going to be nuisance parameters. So the thing that only thing I'm going to really care about until the very end of the process are the clusters. And I'll be specific about that.
You just put a prior on the Bell space, like without substantive comma. I mean, that's an enormous assumption.
Yeah, that's why it got its own slide.
So what's the assumption?
The assumption is simply that it's Poisson with some extra stage to it. Which, okay, so...
Well, Poisson in the number of elements of the cluster, not what's members of what cluster.
Yeah, buried in here is an assumption that the number of clusters is relatively modest because of the Poisson.
Okay, so is the only prior you need the number of clusters?
No, so I get the number of clusters, okay, and then I say, okay, given that number of clusters, pick one with uniform probability. And there's my, there it is, there's my cluster.
Pick a particular cluster.
Yeah.
So uniform over the Bell space.
Yes.
Okay.
So that's just to get us started. This is a prior. So this,
No.
Yeah.
I mean, a prior makes it big.
Yeah, it does. Oh, it does.
I just want to understand the
Yeah.
assumption.
So this is the prior. I'm going to talk about it in a minute. Inside the algorithm is the cluster moving process.
I'm not sure what that means, but I'm just saying I just want to know what the assumptions are.
Yeah. So the big assumption is that there's a modest number prior to the data. There's a modest number of clusters, but that can be manipulated with the zeta here.
Are you doing, or just to be clear on the process, you're going to illustrate this, M, are you estimating, because this is a model-based cluster model, right? This is why it's better than k-means or whatever.
Mm-hmm.
you're taking M and estimating different models with different partitions?
Yes.
And then you're comparing those using what, like?
Posterior probability.
Okay.
I think a uniform distribution over the Bell space.
No, that's not the Bell space anymore, because I've already picked a number of partitions.
Well, but the Bell space. Given five.
It's
five
the Stirling
clusters.
number of the second kind.
Well, okay. I mean, but it's two levels. You're effectively putting a prior on the
Yeah.
uniform prior You put a uniform prior distribution. You've put a uniform distribution or a Poisson distribution on the number of clusters.
The Poisson is over the Bell space.
The Bell space is not a count.
It's a number, yeah, that's true. It's the number of actual clusters. So
Oh,
it's
the number of
yeah,
clusters.
so it's
Okay,
actually
so Poisson on the number of clusters.
Yeah.
And then given a cluster, you have uniform over the particular cluster.
that's right. That's right.
Okay.
So I wasn't clear. So the Poisson picks one of these four, okay, and then inside the one that you picked, so the
uniform.
uniform in here.
Okay. So just one comment, which is, in there, actually, there's enormous repetition in a substantive sense. So if you had 10,000 documents or 10,000 things sorted into 5 categories, and you took one of the documents from category 4 and put them into category 5, that would be those would be 2 different clusters.
Yes.
But from our point of view, a substantive point of view, those are the same for all practical
Yeah,
purposes.
and I do confront that later. Yeah.
And just as it happens, the Bell space is composed mostly of things like that.
Yeah.
So you might actually think about it, I don't know what it would be, but a different prior, right? Because otherwise you're effectively putting mass in particular, you're devoting mass to things that are equal, you're saying they're of equal probability and
Yeah.
they're very much the same. So anyway, it's just a thought, but
Yeah.
I don't know that there's something else that's better.
I will have to think about that. So yeah, I mean, some of them are exactly the same, and you have to eliminate them count-wise.
Yeah.
This entire cluster prior probability thing, if I'm tracking things correctly, you could have done all of this with just without the Dirichlet process. You could have just had a normal random effect on your residual, because this is all doesn't enter into this piece, correct?
Right. The Dirichlet is totally independent.
Okay. So and in your sampler, you're going to have basically 2 phases of your sampler. One is dealing with the Dirichlet, and one is dealing with
Yeah. And there is some housekeeping involved with that, which I'll show you in a second. In fact, it's here. So the first thing we do is we generate a potential sample, cluster, okay? So once we have that, we have a theta C, and that will, in a future step, define the beta Cs and the sigma square Cs. Then we have a set of parameters, mostly Dirichlet parameters, that are independent of the clustering. That is, they pertain to everybody, okay? So the housekeeping is to keep this step separate from that step. And again, this Booth paper is important. So we're going to Gibbs sample the upsilon parameters, which are the ones that are independent of the clustering. Then we generate a cluster, conditional on the values in upsilon, and then accept or reject it with a metropolis step and do that lots. Okay? One of the challenges mixing through cluster space. Cluster space is weird, right? That is, not just in the way that Gary was talking about, like minor deviations, but like big deviations matter as well. So we're going to have to tweak the algorithm with this Jane Neal thing, which I'll describe in a second. But once you have the clusters identified, a lot of these parameters that are invariant to the clustering fall out immediately. So this is like an ugly looking slide, but everything on here is plug and chug. There's not a lot of intellectual work here, other than deriving the full conditional distributions for beta naught, sigma squared, S, and the V's. Okay, so that consumes a bit of time, but it's not complex.
So I thought S was for everyone, but it's
It is. Did I?
no, yeah, but it's scaled as a function of your beta L's, which were cluster specific.
No.
When you're summing over them.
No, it shouldn't be. Which are clusters?
Oh, okay, yeah.
Yeah.
Yeah, okay, you're summing over the
I'm
L's.
summing over them here.
Yeah. Okay.
Yeah. The notation is challenging here, just keeping everything sorted out. There's a lot of Greek letters in this.
Imagine your audience.
And the paper's worse. This is the cleaned up version. Okay, so I also have to jump through the A matrix space. So if I've got A sub t is the current, I propose an A prime from the restaurant algorithm, selected or not with a metropolis decision. And this I kind of said before, but I can be more specific now. The larger lambda is, the more antisocial people will be in the restaurant, right? And if lambda is small, then people like to be together at big round tables. So we also need to generate a lambda in the. This is only a few statements, but this ended up being a bit of work in one of those papers I cited. But it turns out Escobar and West have a very important paper where they give us a recipe for this. So generate this gamma from a beta conditional on lambda and n, and then I can switch out and do another gamma that gamma distribution that generates my lambda. And they've got a nice theorem proof for that. And I didn't know about that paper for a while. And then here's the full conditional distribution for tau, another inverted gamma, of course. All right. So we have to get around this cluster space. And so the way I decided to do this was Jane and Neil have this model. They call it a split merge. And so what you want to do is you want some mechanism for saying, how do you go from this cluster to that cluster? And so what they do is you grab one data case and grab another data case. If they're in different clusters, you merge their clusters, okay, with a probability. And if they're in the same cluster, you split their cluster with a certain probability, okay? And so what that tends to do is it tends to shake up your path through this weird, complicated cluster model space, which is hard to visualize. So we combine that with a random walk around the current cluster to sort of explore high density areas more efficiently. So at the end of the day, we're going to get a probability of each cluster configuration, conditional all the things that I talked about.
So is the split and the merge probability the same?
No, because it depends on the size of the data, right? Because I'm randomly taking two cases, and if that's out of 10,000, that's different than it's out of 10, right? So I didn't say it, but the probability of merging and splitting is a tuning parameter in the algorithm.
And it had to be somewhere.
Yeah. Well, I mean, come on.
I know, I'm fine.
And you do in fact have to play around with it a bit. But what I plan to do in the plan, it's always nice to say what I'm going to do when I write this R package, because you can say anything, is have some sort of an output giving the acceptance ratios or something like that, and asking the user if they want to keep going at that.
So is this,
Matt
is this block sampling the clusters, or is it, or are we going individually, the cluster assignments are being, so there's like one worry is that if you just are, you could have this like bad cycling issue where if you change cluster assignments incrementally for each unit.
Yeah.
Or is this basically, does this in effect actually cluster sample the whole?
Yes, over time it does.
Okay.
So what your point would be a big problem if I only did this.
Yeah.
Right?
Okay.
So in general, I want to do a lot of these things,
Okay.
because that tends to jump over time bigger spaces. Although it's weird to think of, like, it's not this, it's not a real line like all the textbooks have with the distribution, and you're saying it's cluster space.
Yeah.
So this is important secondarily in a sense, because if I'm in a high density area, I want to explore more clusters around that cluster.
Okay.
And I'm more likely to accept them in a metropolis step because they're not going to be a big step down in density. Okay, so do that and then accept it. So finally, once I've done those clusters, I've got a full conditional distribution for each beta L vector and each sigma squared L scalar, right? And this is just regular Gibbs full conditional whatever. So there's nothing weird in there, it's just long. Okay,
Jeff, just like one other quick question, but going back to the clustering. So here, is there like are you drawing the Poisson, like the number of clusters as well in this, or does that just fall out of this?
That falls out of this.
Okay, the split merge. Okay.
Yes, right. So when you do the split merge, you get a candidate, which is more different than if you were just doing this.
Okay.
Oh, yeah, and I should say also, you can also do multiple split merges before you do the metropolis step, if you want to make even bigger steps, although I haven't implemented that yet.
So how do you get for the proposed new cluster, how do you get the betas and the sigma squareds?
So once I have a cluster configuration, right?
Proposed.
Yeah, the proposed. Then I go inside each cluster, and here's the recipe for the full conditional distribution of the beta L vector and the sigma squared L scalar.
Basically, it's just linear regression.
Yeah, everything I'm doing today is just linear regression, right? Undergraduate stats. X prime X inverse X prime Y, well, with a little extra.
So you sample a proposed cluster configuration,
Yeah.
and then sample these.
That's right.
And then you evaluate those three things together in the
Right.
in the step on the slide before.
Yeah, so
Okay, right. So
first step one, you either have or get these guys, right? The non-cluster oriented parameters. You get them from the last step, really. Generate a cluster candidate, right? Right. Then I should have then resample these guys. So I am kind of missing a step. So thanks, Max. And then accept or reject the whole package.
Right. Okay.
So the generating a candidate, you can do whatever you want. It's the accept or reject that is where your prior on the analysis and everything.
Yeah, everything goes in that bucket.
Okay, so the tuning parameters are all about not rejecting all the time.
Not rejecting all.
Or like you're generating a candidate, you're doing your split merge. It's about you want it to be mixing well, but you also want to not spend all your time failing to accept your transitions.
That's right. Yeah.
And so your tuning parameters are fiddling with that trade-off.
Yeah. Yeah. And I usually like it to be between 40 and 60%. There's not a definitive. Well, Kelman has 43%, but I don't know why. Yeah. So till it gets in that reasonable range of rejection. Okay. Where was I? I was there. There's it. Okay, so what I can do at the end is I have cluster probabilities. This is just from Bayes' law, right? I mean, I'm just flipping around the likelihoods. There's the probability, the prior on the clusters that we talked about. And so I can get the probability of every single cluster as the chain moves down the path. The problem is, we've already identified it, is this is an estimate because the sample space is a Bell number big. Okay? And so mixing is really important. There's no evidence that I'm way off the track, but there's no guarantee either. So I put this in bold to be advertised the big challenge here. So here's my application, my last few minutes. So this slide just says terrorism is important. We should worry about it. It's bad. I really like working with terrorism data because it's the worst data I can find in the social sciences, which is a big statement, right? So what's wrong with it, right? Well, it violates every chapter of KKV, basically. You're selecting on the outcome variable. You've got non-granular discrete measurement typically. Insufficient number of explanatory variables. You'd really like to know about the planning details and what things they didn't do and alternatives they had. Missingness is usually non-ignorable. There's a lack of access to classified data, of course. Data is often filtered through government sources. The actors are deceptive. They don't want to be observed. They want to lie. And there's almost always unmeasured clusters in terrorism data. Other than that, it's really easy to work with. But if this were state-level administrators in the state capitals of the U.S., you'd say, well, that's not important enough. Maybe I won't worry about it. But it is an important data problem, right? And so I am going to worry about it, and particularly this, of course, because that's what I'm up to today. So here's a data set you can get: big, allied, and dangerous. Okay, it's bad data. Right? It is it's literally bad data. So these folks built this very nice data set. It's 98 to 2005. 98 was an important year. That was the East Africa bombings. You have the choice of whether to drop out Al-Qaeda or not. There's 2 data sets actually. I dropped it out. My outcome is fatalities. I'm just going to run a linear model. So I have variables like whether there's state sponsorship of this group, where they are from cow codes, the size, which unfortunately gets ordinalized by the data providers, whether they possess territory, the connections in the network sense, and then like some religious ethnic variables with terrible names. Only a political scientist could come up with left no, relig, ethno, right? So these are basically important in terms of religion and whatnot. So I'm going to run this model. I run it for 10,000 iterations, only 5 days. Okay. Assess convergence. Now there's one really weird. So the convergence was fine. Okay. All the parameters. There's evidence that they are not non-converged. You always have to say that sentence carefully. There's no diagnostic for convergence of cluster space, cluster classes. It doesn't exist. And that's really weird to think about. What is the stationary distribution in the cluster class sense? Like that's like almost impossible to visualize or think of, but it's out there. So my evidence that dimension has converged is that all the other ones have. And I'm sorry that's modest. So at the end of the day, I get this cluster arrangement or very slight variations off of that about 45% of the time. That's huge. As it turns out, I've never seen better running this code, but I was happy. So what do I do with that? I guess I could do different things, and I've thought about it.
Wait, sorry.
Yeah.
Is that saying you, over the course of your algorithm, you only had 4 different arrangements explored?
No, it means that of all the things I explored, this or something very similar in the sense that Gary was talking about show up about 45% of the time.
This being what?
There's these cases in that cluster, these cases in that cluster, and so on and so forth.
Oh, the cluster arrangement it divided your data into 4
Yeah,
clusters?
it really liked 4, and it really liked 4 with these cases in those 4, roughly speaking.
And a case is a specific attack?
Yeah.
Okay, but in the slide, and you have 400 attacks or something?
Yeah, something like that. Let me find it.
395?
Where was that?
Forward. 395. 3rd row.
Yeah, right. So way more clusters than the number of known stars in the universe. Other than that, I'm fine.
Yeah, but it's actually fewer than 395 because you're dropping the Al-Qaeda one?
I think that's dropping Al-Qaeda.
Oh, it's already, okay.
Yeah.
And then go forward. All right, thank you.
I'd have to check that, but Al-Qaeda, I think
You-
Al-Qaeda was less than 10% of the total number of attacks, something like that.
Fewer than 100, you get to more than the number of elementary particles in the universe.
Well, thank you for looking that up. Yeah, I'm not there yet.
You're at 395.
Yeah, but it's running,
Oh, I see.
as we speak. Yep. Matt?
Just a quick question on the clusterings that you found. So the output of this is the output just like that you're getting like cluster assignments?
Yes.
Then you have to like be careful with because of label switching in order to say that this is one that you're.
No, there's no label switching problem because every step of the chain, I get an exact cluster.
Okay.
I know the case. That's that curly C I was talking about.
Yeah.
So every iteration of the chain, I get a new curly C.
Yeah.
Right? Something that looks like. Oh shoot! I'm going the wrong direction. Something that looks like that, right? And then I go through all that machination. I take a metropolis decision step that says, do I want to go there or not, right?
Right, but presumably I can cluster them, but then just organizationally, like I would have to number them, number those. They could all partition in the same way, but I might have to number them. I should
probably not number them actually. I mean, it's nominal, right? This is Fred, Joe, Jane, and Bob, right?
Right. So I guess I'm like the way I'm just curious about how you're like the ones that are close to. Right? So there's something like organizational.
Yeah,
Like,
yeah. So I need a way to do what Gary said automatically at the end of the day. What I did is I noticed that this was dominant in this exact configuration, but there were slightly different clusters around, very slightly different clusters that I'm binning to get that number.
Yeah. Okay.
So maybe this would be 271 and that would be 8.
Right.
When you say arrangement, is that 272 specific cases?
Yes.
Or just 272?
No, it's specific cases are here. Yeah.
So it just seems.
It does.
That doesn't seem believable.
I know, and that's why I checked it about 100 times. If you want to think of it more broadly, there are 45% of the cases are very similar, very, very similar to this. Okay, not this exact, but more, 2, 3 off from this. The data really like that cluster configuration.
Given the trouble people have, like if you have a known mixture of 2 components and trying to classify, like this is suggesting that you can get some kind of uncanny classification.
Yeah.
Which
this
the classification literature says you can't do
right,
that.
Right. This is extremely good, and yet I've been suspicious of it since I saw it, and I can't find where I went wrong. And I run this on lots of other data, right, and gotten some. Where is it? 0.21 is pretty high. These are rodents, so this is the other version of the talk. So it is high, yeah, I agree, but it's correct.
Max, what part is slower, the Dirichlet process or the product partition?
The product partition. So the Dirichlet is not that bad. In fact, like I said, we have an R package, whose name I forgot. But you can find it, it's got my name on it. I didn't forget that. It's both good and bad when you forget what the name of your R package is. It means you have a bunch of them, right? So there's different things I can do given this. And so one of the things I thought, well, okay, that's a strong enough result. I'm going to take that temporarily as fact and just run a multi-level linear model, right? So here is a regular standard linear model. And here I have, 4 random effects defined by those 4 clusters. And the interesting thing is this cluster is much deadlier than the other clusters, and that was dominated. I looked; it was dominated by Islamic groups. So then the orangey stuff is just, hey, it's different, right? So the literature seems to think that it's important that when terrorist groups hold territory, right? But it's less important under my classification, for instance.
Is it? I mean, so because the clustering is also going to pick up on the differences between in the betas, not just, So it would be. So have you looked at all at what if you just broke up this by separate models?
Yeah.
For each one of the 4.
I've done that. I'm undecided on what's the better.
I just don't. I mean, I don't know.
So I call everything after this post-processing.
Yeah.
Right. And so yeah, I've thought about that, and I should have done it for today. But you can take that information there and do different things with it, right? Including have 4 columns of betas, which would make an IR journal happier.
Yeah.
What's the histogram? Your outcome is number of deaths?
Yeah.
What's a histogram of that look like? Is it basically you have a huge clump of outliers?
Yeah, it's right-tailed. It would be more right-tailed if I had Al-Qaeda in there, of course. So ongoing activities. I'd like to wrap this up this summer. Thanks for the comments. I need to make it more efficient. I'll always say I'm going to make an R package. That gets your grant score higher. Excuse me. I'm still thinking about the efficacy of that probability calculation, which is an estimate because I can't do the whole Bell space. One thing I can do is if I can have an a priori upper bound on the number of clusters, life gets way easier. Okay, so if I go to a conference on terrorist data and somebody says, well, you'll never have more than 8 clusters, or I find a paper that says that makes my life way easier both in estimation and in exploration of the Bell number space.
It's going to be a function of n, right?
Yeah, I would think
It
so.
can't be bigger than n.
Well, it's n now, right?
Yeah, but I mean, statistically, even if you knew what the clusters were, you would combine them if it were close to n.
Yeah.
So the right number is n divided by 5. You know what
Can
I
I
mean?
quote you on that?
Yeah, so it's something like that, right?
Yeah, I'm going to put that personal communication. Put that in paper. Gary said I
But
could
you could
have.
put a prior like that, like.
Yeah. Well, is it a prior? No, it's not a prior. It's a parameter you're fixing, right?
Is it a hyperparameter?
Yeah,
You're like approximating, right?
Yeah, but it doesn't show up in the model. It shows up in the exploration, right?
Have you done simulation studies on this to see if you recover
Yeah.
anything?
Of course. Yeah.
And simulation on data that looks like the terrace data?
I tried, yeah. I mean, simulated data humans are bad at making up data, but yeah, I tried to make it look like something like the terrace example with correlations, and I threw in some debris, random effect sort of stuff that, that the Dirichlet could handle. I don't have that in the paper, I don't think, but I should. That's a good reminder. Thank you. Did I get through my list? Oh, I want to develop a cluster space convergence diagnostic. That'd be really neat. And maybe a bigger, well, I probably don't need a bigger example than 300-400. And that's it. Are we done?
About 15 minutes for questions if we want.
Because everybody held back during the talk.
Just in the example, I mean, you didn't really touch on it. So do you have a sense about what the Dirichlet process is doing for you in the substantive example? Is it?
Well, yeah. I mean, what I found is that in other papers that you saw is that terrorism data. Terrorists are imitative. They're clumpy. They communicate. We know that there are unseen groupings in those types of data. And so I don't think I have to rip apart the model here, because I've demonstrated in other models that these kinds of data are improved by the Dirichlet process. So I did what I think is a bad thing, which is over that period of those papers, George Casella would fly around the world and give a talk on these sort of models, and all of his examples were terrorism, and he started getting really interested in terrorist data and started reading about it, and he liked it when people asked him substantive political science terrorism questions. So I took a perfectly good, if not amazingly good, statistician, and I turned him into a political scientist. Yeah, I know. There's a special place in hell for me.
Can I ask you about your first slide?
You mean the title?
Second slide.
Because I was hoping you had a better title for me. Or anybody. Send me an email with a better title someday.
Talk about rest. Sorry, it's third slide.
Oh, this is still bothering you.
Yeah, well, I just don't understand. So that the first model is a coherent Bayesian model with some, given some prior on beta. The second model is let's suppose you have some prior on beta. It's not exactly a Bayesian model, because, at least as I understand it, a Dirichlet process is not a proper probability distribution. It's a class of probability distributions or something like that.
Yeah, which you average over numerically.
It's a probability distribution over
but it is not.
There's shorthand there. That should be psi I is distributed according to F.
This is
F,
yeah.
But then no, that the psi I should be distributed according to F, and F should be a single draw from your Dirichlet.
Yeah. Yeah.
But you've collapsed it.
But that's still.
Yeah. But actually, no, that's true for one iteration of the sampler. But so I'm averaging across.
But your model, the implied model is that you have a distribution on your random effects, but you don't know what that distribution is.
Right.
that distribution is in turn sampled from your Dirichlet process.
That's right.
But right there, you have it as your individual random effects are being sampled from the Dirichlet process. But the psi are not distributions in their right; they're specific values. So
That's right.
You need an intermediate like psi I distributed,
Yeah.
drawn from F drawn from DP.
Yeah. That's better.
But still, unless I didn't understand what you said, well, I didn't understand what you said, but, so let me just say what I said originally. Sorry.
Makes me believe I understood.
So, to have a proper Bayesian model, that has to be a prior, and the prior means that thing after the tilde has to be a proper probability distribution.
Yeah, and that's what the Ferguson and Antonian papers demonstrate. Yes.
What's the probability distribution?
It's a probability distribution over probability distribution.
Yes.
That's true, so,
Yes.
but it has to be a probability distribution over psi. No, go back. Okay, good. I don't want you to talk about samplers, estimation,
Okay,
approximation.
fine.
MCMC. The whole problem with the whole MCMC literature in the 1990s is they stopped writing down models and they started writing down algorithms. Right? We need an algorithm, but we first need to figure out what the model is. So to me, that's not a prior distribution. Prior distribution is something where you have one parameter, it has to integrate to 1, and it has to always be above 0.
Yeah.
And that thing is not that.
Yes, it is. And it's provenly so.
So what is the, it is?
Yeah,
I thought you told me it is the thing from which you can draw a probability distribution.
that too.
Oh, so it is actually just a probability distribution? So if you go back to the previous page, sorry, one more time. And you set lambda equal to, 4 and G0 equal to 7, and you plot the thing and you integrate it, it integrates to 1.
G0 is something like a normal distribution.
Yeah.
So
Well, that's what I mean.
I think, let me try again. Psi I is a real number.
Is what?
Is a real number. Like psi I is in the
It's drawn, yeah.
It is drawn from some distribution. But DP,
What do you mean it's a real number? What does that mean? It's
On the real
like
number.
it's a number like 5 or 20 or something like that.
well,
It's a real number.
so the space of possible values of psi are
Psi is like when you think of a model for when you think of a multi-level model, each I ranges from 1 to n,
okay.
and so we have n random effects.
Non-unique random effects.
Well,
Okay.
that's because your DP is going to give you a discrete measure with probability 1.
Yes, exactly.
But going up to the top line, I see, because
Top line is totally fine with me, because I just
the
said.
top line isn't totally fine with me now that I look at it, because you're saying that the psi I is not a residual. You're saying that I doesn't range from 1 to n?
Sure.
Or the psi I is
So-
distributed normally 0
so-
tau squared, but they're not IID?
So in this case
Yes, they
here, okay, just regular random effect, I've got 300 cases binned into 10 groups, and I know that mapping from individuals to groups.
There's no 10 groups there. There's no groups at all.
Whatever. Yeah. No, for random effect in the convention.
Right,
But
groups
you're
there.
not indexing your groups.
No groups.
He's leaving his groups implicit.
Yes,
That's why
I am
I'm
doing
having
that,
trouble
yes.
with
But
it.
I see, Gary. I mean, it's just that
You
you
mean
can
tau has a subset?
DP. You can draw like psi I from. You can I can go simulate it for you and show you that it is.
It integrates to 1. Right?
Yeah, it's a distribution. I mean, it's just.
As long as you fix
No,
G0.
psi I is
lambda.
not a distribution.
No, psi I is a draw.
No, you can draw. I say you can draw it from it. You can. I can draw. I can simulate it.
DP needs to be a distribution.
But DP is not, DP, you cannot get a real number out of DP.
No, we need a real number.
This is just a short. I mean, but this is just. I mean, this is how people shorthand
No,
this
it's-
particular process.
I think
Well-
I think the problem with it is you end up in these conversations.
So
Well,
right.
I'm consistent with the literature at least.
Yeah, I think.
With
So
random-
show us but Luke,
Really?
now I understand the question to ask Luke about the point that he was making. So you have a coherent way to write that down that would satisfy Jeff and me and Matt. So what would that be exactly?
Now we go. Now we talk.
I'm gonna take a picture of this.
Wait, lambda? What happened to psi?
Oh, sorry.
So psi is distributed as f. So
Yeah.
just so I know what's f.
F is a probability distribution. So this is a probability distribution.
Like what?
Like a
Like a
normal,
normal
Over-
zero.
a normal with some.
over the reals.
Okay,
Like,
over the rail.
and
that's
in
fine.
particular, because it's coming out of this, it's a probability distribution with an infinite number of discrete probability mass points.
Yeah.
So this distribution looks something like this. If this would be a, and then there's like little dust here like that. And
Okay.
so we're saying psi I, we're drawing it from this, which means that, and that's when we're talking about subclusters, that's when you draw from this, you're gonna end up with like, there's a high probability of, say this is like 3.2. You're gonna have a lot of your psi I are gonna be exactly 3.2. Some of them are gonna be like 10.1.
Okay. So then I would just ask the question, suppose we did what is the compound distribution of F and DP? So that I get to know the prior on psi.
It's
Actually, if
it's the restaurant.
Yeah.
So
if you
probably
actually,
positive.
if you marginalize out F, you just get G0. This is your base measure. So in fact, if you draw psi I, a single psi I, if you first draw F from a DP and then psi I from an F, I believe you just get your base measure back.
Yeah, that's for a single iteration.
Single draw.
Yeah.
You mean for observation I?
But now that this is tying together all your observations, right? So a single observation would be distributed according to G0, but if you have multiple observations, because they're all coming from F, this is like a latent parameter which is going to create correlations among your observations. In particular, say you have two observations. If you draw one observation and you get 4.8, you know that your next observation has a high chance of being exactly 4.8.
So then this needs to be changed a little because that I can't be there, right?
No, that I could be there.
But if the I is there, then it's basically IID.
Yes, these are IID, or actually, but this is where we get to the, I think you're saying that these are IID, but that's where I'm not exactly sure of your model.
No, they're, where is it? It's a dependent exchangeable sequence. Right, so it's exchangeable in the Bayesian sense that
But conditioned on F, once you have your F,
yeah,
then they're IID.
yes.
Once you have F, they're IID. But
Yeah.
you don't have F.
Well,
Right, so
you
you
do
draw
as
that.
soon as you plopped out a partition.
So it's probably not quite the right way to write it because you still have psi of I that is treated separately for all I.
Yeah, so like but it's a two-step data generating process. This I equals 1 to n. So step one
I
is get
see.
a distribution, and then step two is get all of your ni's.
I see. So that's you draw a DP once. You
You
draw F once.
draw a single F, and then you use that F multiple times.
Oh, I got it. Okay.
And that's what creates dependency among all of these little size.
Right,
okay.
but the size are non-unique, so they determine a
I
random
see.
effect.
So when Jeff says non-unique, he means
Discrete.
what you mean by non-unique, Luke, is that there's one F for all the observations, and then there's IID observations from F.
Yes,
Yes,
that's my understanding.
right,
Like,
right, and then the sampler averages that all out, does the integral.
And I don't know what that is.
That's just deeply, deeply irrelevant with respect to the model, even though that's the way it does its thing. right?
Okay.
So I'm just trying to
But see-
understand.
but
If
see-
you go back to that page that makes me comfortable, I'm only comfortable on page 3 of your slides, right?
H2.
So, right, because you have you basically, as you said, that second model is a linear regression model with a different prior.
Yeah.
So the prior then, so the interesting thing about the prior is that it's creating a dependent prior over observations. That's sort of the main thing going on
Yeah.
here. And
You could
this
call
is, and what Luke wrote down is sort of the particular way that it's creating the dependence. Right.
Yeah,
Okay, and now you can go talk about the algorithm.
so I obviously failed on these slides, right? Right, so the really important one that addresses your concern, these papers prove that this is a distribution in the Kolmogorov sense. That this process produces a distribution.
That is when you draw F from DP.
Yeah,
Yeah, that's cool with me.
yeah.
I just wanted to, I think that now, to me, is a coherent Bayesian model. So
Mhm.
that's what they proved, basically.
Yeah,
So that's just a little extra notation that would help, I think, right at the beginning.
okay, that's very good.
And in practice, you made a claim about on that slide too, right? You said that the second Gill component is not substantive,
Yeah.
but it is
Helpful.
It's helpful In other words, between those two models,
Yeah, so,
ceteris paribus, whatever it is,
yeah.
we all should be doing the second.
Yeah, so a way to satisfy that question and Gary at the same time, suppose you were in this world, okay, and you knew that people were binned, cases were binned, and you ignored it, right? So classic multi-level model context, that variability falls to sigma y, right? Okay, so
Yeah,
now,
that model ignores it.
no, I'm saying you didn't do that, but you did have groupings, okay?
Well, I'm just saying, the way it's written there are no groupings.
No, because, well, okay, I should have, it's implied, to use Luke's exact phrase, right? So why would you do this if you didn't have groupings to assign people to estimate the differences? Right, so
You have
if
known groupings, and then you have
No groupings.
unknown, unobserved groupings that you then model through the distribution
Exactly.
of, hyperdistribution of a discrete number of
that's right,
unknown.
right. Yeah,
So-
so you average over a family of distributions that you get to define.
So the implied thing is that 0 is really a variable, and it has a subscript, right? And it varies over the groups.
I just put this here because it's conventional.
Yeah,
right?
but I think that's, when you're saying it has groups, I think you mean it's not 0. It's just there's let's say, I don't know, theta sub I, and theta takes on only, or no, not theta sub I, it's theta sub j, and j takes on like 5 values
Yeah,
or something.
so if you run LMER in R,
Uh-huh.
right, it's got this assumption built in.
I mean, I think Gary, the thing you're missing is there's just like there's this like implied here is like a W matrix in front of the psi that converts
Yeah.
a short vector, the vector
It's like my
K
A matrix.
size into an assignment of like for each. So you're
Into
saying
five
Matt,
items.
that is exactly.
And
Yeah,
that
it's-
subscript, the subscript I on the first page, I'm uncomfortable again.
yeah. So you just
The subscript I
This.
goes over 5.
yeah, over five, yeah.
This right here.
Yeah.
Psi I, right, is
okay.
equal to eta j if the
I
ith
got it. Okay.
case is in the jth group on that iteration.
Okay.
It's just a compact.
Okay.
It's just a compact way to write.
So I would, I mean, so my suggestion would be that like if you lose people on the first page, then,
Yeah.
you know, unless you're really interested in the details, I mean, even if you are, you lose everybody. So I would make the first page overly obsessively detailed so that it's absolutely understandably and correct, and then have this and say, this is my summary of that, and then I would get it.
Okay.
I would also, another suggestion is just go to the clustering, and you're basically like, if I'm understanding your talk right, you started your talk by talking about your residual errors, and then we got to the middle of your talk in terms of the
Product partitioning.
the partitioning
Yeah.
later. But by that point, we were all struggling with the residual errors stuff. You might want to just jump directly, because I think you can talk about all the partitioning stuff without making reference to any of the Dirichlet process stuff. And then say, oh, by the way, you can
Yeah.
actually improve your residual errors. Here's this extra piece
Yeah.
that sort of accounts for it, and then
I've thought about that as far as the paper goes. Yeah, that's probably the right way to write it.
Instead of clusters, because these are the
I've got to
subclusters
dump
talk
that
about
phrase
that-
subcluster.
It's segmentation, right? It's like
Yeah,
error,
it's the-
you could say error segmentation or
Yeah, it's the table
random
assignments.
random segmented random effects. I don't know.
but in terms
Whatever
of
it is, you're mixing up clusters, and then the idea of you're priming the audience to think of a hierarchical model if you're talking about.
Yeah, I mean, I do say at several points, these are orthogonal processes, but the language spills over, is I think the problem you're alluding
To
to.
use a restaurant analogy, this is like the amuse-bouche. This is like the hors d'oeuvre, and then we forget about what the main meal is.
Oh, no, I can improve upon that. You and I can sit at the same table, but we're not required to order the same dish.
There you go.
you don't want to go down that direction, because then everyone will think you're talking about Indian buffet processes.
Right.
That's true, yes, yeah.
So
This is the last comment, by the way.
Alright. Oh, then it shouldn't be me.
Go ahead. You already started.
In terms of the meaning, in your terrorism example, you have these clusters, but then for different clusters, the Dirichlet process piece is basically saying that your residual errors are correlated for some of your units across clusters. Basically, you're saying
one of the events here and one of the events in this other cluster are somehow tied together with a common residual on number of fatalities.
I'm uncomfortable with the residual. I would say they share the same latent, unobserved effect.
Which is either
Or they-
which is elevating or suppressing the number of fatalities, both of these
Yeah,
things.
yeah. But and then I average across that, right? I mean, the sampler averages across that effect. So, like, one draw of the sample is not the truth, right? I'll never get the actual truth.
Right.
But by averaging over a set of possible truths, I average out the effect, the deleterious effect of ignoring that latent heterogeneity.
Is it latent heterogeneity or latent like unobserved correlation?
It's latent heterogeneity. I mean, it's probably correlated, but you have no idea, and you can't produce that correlation. The key is, though, that in our case, it's on the random effect. In fact, there's a proof that if you put it on the beta parameters, they're biased, although that's been done.
Okay, great. Thank you so much.
Thank you. Thanks, Luke. That was really helpful. Good.